welcome to another Turing Mock Interviews. My name is Jose and I am tech lead at Turing and I'm from Montreal, Canada, and today I'll be interviewing Tituan for the role of an experienced ML scientist. And to get started this, I would like to hear from you, Tituan. But before everything, how are you doing and how is your day doing so far?
So hi Jose, thanks for having me. I'm doing good and my day has been going great.
All right, great. Could you please introduce yourself and tell me a little bit more about your background and your professional experience?
Sure. My name is Turing Mock and I'm based out of New Delhi, India. I graduated from Delhi Technological University with a degree in mechanical engineering. Although my core branch was mechanical engineering, but I had an interest in data science and machine learning, so I wanted to switch into a tech career. And I made progress in that direction itself. So talking about my professional experience, I have had internship experience with two unicorn-based startups in India. One is in logistics domain and another is in the fintech domain. Apart from this, I have also worked for a luxury fashion tech company based in US. And after that, right now I'm working as an ML scientist at Turing.
Nice. Really great. Thanks for sharing. And could you please tell me about some interesting projects, ML projects that you have been working on?
Sure. So one of the projects that I would like to talk about is called RTO prediction, which I worked in one of my previous organizations. So RTO stands for return to order. So whenever you shop online, there are several options for making payments. Either you make a payment in advance, then other than that, you have a cash on delivery option. When the parcel arrives, then you pay the delivery guy with the cash, right? So whenever you place an order, there are chances that the order can get cancelled. But let's say if the order has been shipped by the company and it's sitting in the warehouse of the shipping company, and at that point the user cancels the order, the shipping company or the logistics company had to bear the cost for shipping it back to the vendor, back to the basically platform where it was originated. So we wanted to minimize that cost. And other than that, what would have had happened when the delivery person had reached the door of the customer, and at the door the customer refused that he doesn't want the order anymore. So they couldn't do anything in that case. So the order would have to be shipped back to the vendor, and the wages that were paid to the delivery guy was also, had to be given. So there were a lot of losses that were incurred due to this phenomena. This is known as RTO, return to order. So this is something separate from like when you take in the order, you try it out, you didn't like it, and then you place return. That is something that is completely different. But the thing which I explained earlier is known as return to order. So we wanted to minimize that return to orders. So at the time of manifestation. So manifestation means when the parcel arrives at the warehouse of the shipping company. So basically I worked at the logistics and shipping company. So when that parcel arrives, it is scanned. That point is known as manifestation. The order has been manifested. Right. So at that point of manifestation, because beyond that, the shipping company had to bear the costs of shipping it and making sure it reaches the customer well and good. So at that point, we had to predict whether the parcel would be RTO'd or not. So it's a binary classification problem. The chances are that it would be RTO'd and it would not be RTO'd. So there are two options. That's called binary classification. Binary means to write.
Got you. And so, you learn from the past, right? This is a classical ML algorithm, right? You learn from the past.
We learn from basically several things. So there are two types of features or variables that we use. One is customer-centric variables. Let's say a customer is old customer. He has shopped from us previously as well. And if we look at his order history, he has a tendency of canceling orders at the last moment. So we use those customer-centric features. Again, as you said that from the past. Other than that, we have product-centric features as well, right? So from which company, what is the product? What is the category of the product? From which brand is that product, or from which seller is it coming? Let's say if the if the seller is selling a particular product at a particular price, but then again some new seller comes up that is offering the same product at a cheaper price, so the chances are that the user would cancel that order and go for that vendor, right? So there are two types of features. One is customer centric, and another is product slash the everything related to the product centric. So we use these features collectively to build a predictive model and tell what are the chances of this order being RTO'd or not. So some of the things that I remember about that is that that's a very low chance of order getting RTO'd. Like you can say a 2 in 100 would get 2 orders in out of 100 will get RTO'd. So it's a very skewed data set. Very few classes belonging to the RTO class, and most of them belong to not RTO class, right? Gotcha. So that's another problem in binary classification that we try to solve. Yeah.
Cool. All right. Thanks for sharing. That was really interesting. All right. And let's now talk about ML. Okay. What is statistical significance?
Okay. So let me explain in simple words. Statistical significance means if an event is occurring, whether is it occurring by chance or there is some significant reason, or there's that event is something significant. For example, if I toss a coin, right, we say that the probability of occurrence of heads and tails is 50-50, right? 0.5 probability of occurrence of head and 0.5 occurrence of tails. But let's say I give you a coin and tell you to toss it 10 times. So is it certain that always you will get 5 heads and 5 tails? That's not certain, right? You could get 6 heads or 4 tails, right? So can we say that, hey, you told me that the probability of occurrence of head is exactly 50%. So if I toss a coin 10 times, I should get 5 heads and 5 tails. But when I do it manually, I get 6 heads and 4 tails.
It's impossible.
Does that mean does that mean whether the coin is biased? Is heads something heavy? The heads on the side of head is heavy, or tail is light? Is that a case? We cannot be certain just by 10 examples, just by 10 tosses. So what we need is a set of experiments to be done. This is known as law of large numbers. So if you toss 10 times, you might get 6-4. But if you toss the coin 10,000 times, you see the probability would converge towards 50%. You would get 51% heads and 49% tails. And as you increase the experiments, it would go even further close. 0.5000 or 50.000% of heads and 49.9999% of tails. Mm-hmm. So it eventually converges into the 50% rule. So that's what we try to test using a statistical significance, whether an event occurring is statistically significant or by chance. So tossing a coin and getting 6 heads and 4 tails is probably by chance and not statistically significant.
Move on. What is cross validation? Okay, and why it's important in supervised learning?
Okay, so when you build a machine learning model, you want it to perform well, not only when you are training the model, but also when you have deployed the model to the cloud, or whenever you are using the model after the training. You want it to perform consistently throughout for a certain period of time, obviously, because there's something on data drift, so we have to train the model again. But anyway, for a certain period of time, you want it to perform well, as good as it is performing on the training. So how do you make sure that it is going to perform well in the future as well? So when you have a data set, you divide it into 3 parts. One is known as training data set, one is known as validation data set, and one is known as the testing data set. You do not touch the testing data. You keep it aside. You train the model on your training data set, and you test your model on that validation or holdout set. That's called validation for you, where you test your model on unseen data. And what cross-validation means is when you use separate iterations of the basically validation or the training data set. For example, I divide my set into 5 parts. I train on first four and test on the last part. Similarly, now since I divided into 5 parts, now let's say there are 1, 2, 3, 4, 5. I train on 1, 2, 3, 4 and test on 5th. Now I'm going to train on 2, 3, 4, 5 and test on 1. Then I'm going to train on 1, 3, 4, 5 and test on 2.
Gotcha.
After that, I'm going to train on 1, 2, 4, 5 and test on 3 and so on. So that's cross validation.
Okay.
It's a technique we do to make sure that the model is performing well in all scenarios once it is from the training phase.
Okay, got you. All right. And next question is, what do you understand about PCA? Okay, what is principal component analysis?
Okay, so it's a mathematical heavy topic a little bit. So PCA stands for Principal Component Analysis. So it's known as a dimensionality reduction technique. In data science, we come across a problem known as curse of dimensionality. That means when you have very large dimensional data, that is, we have way too many features. We have way too many variables which are changing, right? Variables change. So then that leads to something known as a curse of dimensionality. It causes several problems. Training delays, the time of training would take very long because there are way too many variables that you have to control and you monitor, right? Apart from that, if the model is slightly biased towards any particular variable, a small change in that variable would reflect towards your output. So you want to make sure that you have minimum variables that are explaining your target variable well. So PCA is used to solve that problem and reduce the dimension of your data, reduce the size of your data, and keep only those variables which are most important for your target variable. We use it using something known as variance explanation. Basically, the variables which are explaining the maximum variance in your target variable. Now, in simple words, if I say, if there's a change in let's take an example. Let's say we have a data of children, right? We want to predict the BMI or basically any health criteria, which is dependent on weight, height, etc., or diet of the child, right? So you want you have n number of features, and you want the relevant features which are explaining the variance well. So if I change the BMI, if I introduce a change in BMI, what variables explain that particular change in the BMI would be those which are explaining the maximum variance. So we want to select those variables. That's what we try to do using PCA. So we can also go into deep in mathematics of how it is derived and all. So again, that's optional. If you want to go, we can go there as well.
Oh, we have a chance for that. Yeah. All right. Let's move on. Okay. My next question for you is, what do you understand about the difference between forward and backward propagation?
Okay. So in neural networks, so it's a generally a topic of neural networks. So what happens in forward propagation, where you do a weighted multiplication of your value of your neuron's weight and the variable that you are considering, right? So you call it a forward pass. Let's say we initialize the neuron weights randomly. We create the regression equation or basically the equation that we want, weighted sum equation, and we pass it. We give it a forward pass and compare it with the target variable. We compute the loss, we compute the errors, and we move that error backwards so that our neural network could learn from that errors and sort out those mistakes that it was making. So when we make a prediction or when we give the first output, it is known as a forward pass. And when we compute the loss or the error and move it back to the neural network, that is known as a backward pass. So the algorithms that are controlling this are known as forward propagation and backward propagation.
Cool. Yeah. All right. And so, as you mentioned, neural networks, okay? What are the loss functions in neural networks?
Okay. So loss function is something which computes your loss or error, right? So if you are making a prediction, you want to check how accurate is it, right? So let's say we are solving a problem of predicting house prices, right? What is the price of this house going to be given a set of variables, obviously? Let's say the actual price is $100,000. and your model gives a price as $50,000. So you have an error of 50,000, right?
Yes.
Because it was supposed to be 100,000, but your model predicted 50,000. So the difference between the two, the actual value and the predicted value, is known as the loss or the error. So the functions which map these errors or losses are known as loss functions. Some of the prominently used loss functions are mean squared error, mean absolute error. These are some regression-based loss metrics. And in classification, we use binary cross entropy or cross entropy. So these are some of the prominent loss functions.
Could you please explain me how gradient descent works in linear regression?
Okay, so again, I'll explain in layman's term. Consider a hill. Consider a person who is, or a ball rolling down a hill, right? So right now it is at top and it'll come down and stop at the bottom, right? So valley, a U-shaped valley, and a ball rolling down that particular valley and stopping at the bottom. So that's exactly how gradient descent works. So we talked about loss functions, right? Loss, we talked about error. So we want to minimize that loss, right? We want to minimize that error so that our predictions are more and more accurate. So in linear regression, generally we have a loss function which is mean squared error. So mean squared error is a convex function or an upward opening parabola, which is again a U-shaped curve, right? We start somewhere at the top of the curve. Now we want to reach the bottom of the curve because the bottom of the curve has the minimum error. Because since the loss function is a parabolic function, upwards opening parabola, the minimum value would be always at the bottom of the parabola. So we want to reach that bottom part. So the gradient descent algorithm helps us reach that bottom. So how does it function? So mathematically, first we compute the prediction or hypothesis. We compute the difference or we calculate the loss, which is the mean squared error, R value minus the actual value whole squared divided by the total number of inputs, and we take the sum of it. That's the mean squared error value for it. Then we use something known as a gradient descent algorithm or the update rule. So we compute the slope of that function using again dw by d theta or dx by d theta, where x is the loss function and theta is the weight with respect to which we are differentiating. And we perform the update rule, that is differentiate that the new value of the weight equal to the old value of the weight minus something known as what do you call it? I forgot the name. Learning rate. So learning rate is something that makes sure that we are learning at a certain rate. It's a parameter. It's a hyperparameter that can be tuned, right? Learning rate multiplied by the differential of the loss that we are calculating. So once we reach the bottom, mathematically, if equation follows y equal to x square, the slope at the bottom becomes 0. So the differential would automatically become 0. So when your weight doesn't, stops to update, that means you have reached the bottom. So that's what gradient descent, that's how gradient descent works. So basically it allows you to reach the bottom of the loss function. Advantages, it is basically you can say better than direct differential calculus, because that can be complex when we want to code it and we want to higher level computations. It can be computationally expensive.
Okay, and as we are talking about error, and you talk about variance. So what exactly is variance error?
Okay, so variance error means basically error comprises of three parts: a bias square plus variance plus irreducible. Irreducible is something that is due to noise and we cannot alter. So the variance error is when your model starts to overfit the data. That means whatever training data that you have fed the model, it is learning it too well, or it is just cramming it up, and it is not able to generalize well on unseen data, which we call it validation or testing data. Again, a real life example analogy could be a child learning for an exam. He is, let's say, learning a particular topic. It is just remembering the topic and not learning the concept well. So when he goes into an exam, the concept might be same, but the question could be different. But since he was remembering instead of learning, he would not be able to generalize those concepts well on unseen problems. So that's exactly what happens in variance error or overfitting. Your model remembers the data, the training data, but is not able to generalize well on validation or testing data. In that case, we observe very low errors on the training data, but very high significant errors on unseen data. We want our model to perform well on unseen data because it will be deployed or used in real life.
Makes sense. All right, and move on. How would you deal with classification on nonlinear separable data?
Okay, so first let's get what is linearly separable and non-linear separable. So linear separable means which can be where two classes can be class one, but could be multiple also. Let's take an example of two classes where two classes can be separated using a linear curve, could be straight line or a plane. The straight line separating class one, class two, that's linearly separable. But when there is an intermingling of classes and you cannot pass a straight line to divide the two planes or divide the two parts, that's called non-linear classification case, where we really have to use some complex algorithms such as decision tree-based algorithms or k-nearest neighbors or random forest. So basically tree-based algorithms or ensemble-based algorithms that deal into this what do you call it, non-linear classification problem. Decision tree generally can solve this problem using what is known as orthogonal decision boundaries, where in every breakpoint or in every step it creates an orthogonal or a perpendicular decision boundary, and at the very next step it creates another perpendicular to the existing decision boundary. And when we are done with the tree, we get something basically a non-linear decision boundary which can separate the two classes well.
Gotcha.
So that's how we deal with non-linear boundaries.
All right, that was my last question. Okay, thank you, Titwan. It was really nice to speak with you today. Okay, and before I let you go, okay, if someone aspires to be an ML scientist, okay, what steps they need to cover? What do you recommend them? Which language they need to learn first?
So generally, Python is the one that organizations use, but R also works well. So I've seen some of the organizations using R as the programming language for data science tasks, but mostly Python is preferred because Python has n number of advantages. But given that R is also a statistical language, so R can also be learned. Nice. So these two would be my recommendation.
Nice. All right. Thank you for your time, and I hope to see you again in the future. Okay. Yeah. All right, and to everybody else, thank you for tuning in this mock interview series, and I hope you enjoyed this video as much as I did, and I'll be back very soon with many more episodes covering different tech stacks and language. And if you are looking for a specific mock interview, please drop your message in the comment section below. And until then, don't forget to subscribe to our channel and give us a big fat thumbs up for this video. Create your profile at Turing if you don't have one, and keep learning, keep your learning speed alive, and I hope to see you all in the next video. Take care.